Welcome back, guys. We are looking at another error problem involving a Maclaurin series. This time we're asked to determine the degree of the Maclaurin polynomial required to give us an error less than a certain value. So we know what we want the error to be. We're just wondering how many terms do we need to take to get the error that we want. Well, in order to do that, we just need to find an expression for the error, and then we'll set that error to be less than 0.0001, and then we'll just solve for n. We'll solve for the degree of the Maclaurin polynomial. So first of all, let's find the Maclaurin polynomial for f of x equals natural log of 1 plus x, and we're asked to approximate this function near 0.5. So I think it would make sense to, since we're asked to find the Maclaurin polynomial, let's find the Maclaurin series for this function. First of all, I notice that the derivative of natural log of 1 plus x is 1 over 1 plus x. And that is a geometric, or that is a function that can be represented by a geometric power series. I can, instead of adding x, I can subtract a negative x. So I can write this as the sum as n goes from 0 to infinity of a times r to the n. A is 1, r is negative x. So this is the sum as n goes from 0 to infinity of negative 1 to the n times x to the n. Now that's the power series for the derivative of f. To get the power series for f, I need to anti-differentiate that. I'm trying to get this series for f back. So natural log of 1 plus x is the antiderivative of the derivative of f. And so we take the antiderivative of this infinite series term by term, and we get this. The antiderivative of the sum is the sum of the antiderivatives. So you can pull that integral operator inside and just take the antiderivative of x to the n. So we add 1 to the exponent and divide by the new exponent. Don't forget to add c. Now, natural log of 1 plus x doesn't have an arbitrary constant in it. So in order to find the value of that constant, we're going to need to substitute a value of x that would make this the sum of infinitely many zeros. So if x was 0, this would be the sum of infinitely many zeros. So substitute x equals 0 on both sides of this equation. Then we'll have natural log of 1 plus 0 equals the sum of infinitely many zeros plus c. Well, we know that the natural log of 1 is 0, and so we just get c equals 0. So now we have natural log of 1 plus x can be written as this series. It's the sum as n goes from 0 to infinity of negative 1 to the n times x to the n plus 1 over n plus 1. So if I expand this, when n equals 0, I get x, or negative 1 to the 0 is 1. This is x to the 0 plus 1, or just x, over 1. And then it's alternating. When n equals 1, we've got x squared over 2. When n equals 2, we get a negative 1 squared is positive 1. That's x cubed over 3. Then we have x to the 4th over 4, and so on. X to the 5th over 5. And the question is, that's our series. How many terms of that series do we need to take? What's the degree of the polynomial? Where can I stop so that the error in using that truncated Taylor series, or that truncated Maclaurin polynomial, is less than 0.001 at x equals 0.5? So in order to do that, we're going to look at our error. The error of the approximation for an nth degree polynomial is equal to this. It's the order of the next derivative or the next order derivative, evaluated at a over n plus 1 factorial times x minus the center of the series, which happens to be 0 to the n. And we're told that x equals 0.5. So the remainder at 0.5 will be the absolute value of the n plus 1th derivative at a times 0.5 to the nth divided by n plus, or that should be n plus 1, to the n plus 1 over n plus 1 factorial. Now that is definitely less than or equal to this, the maximum value of the error. So we have 0.5 to the n plus 1 times the maximum value of the absolute value of the n plus 1th derivative all over n plus 1 factorial. Now this is the maximum value of the n plus 1th derivative on the interval from the x value, or from the center of the series, which is x equals 0, to the x value where we're evaluating this. So this is the maximum value on the interval from 0 to 0.5. So we need to find, we need to find the absolute, or we need to find the n plus 1th derivative of this. We need to find a pattern for the nth derivative. Okay, well that's easy enough. We know how to find patterns for nth derivatives. We do that often whenever we're working with Maclaurin series. So let's find a pattern for that derivative here. I've got natural log of 1 plus x as my function, and then I'll take the first derivative. That's 1 over 1 plus x, or I could write that as 1 plus x to the negative 1. Second derivative, that's negative 1 plus x to the negative 2 times the derivative of the inside, which is 1. Then we'll take the third derivative. We have a negative 1 times negative 2, x plus 1 to the negative 3. You see the pattern? Fourth derivative, negative 1 times negative 2 times negative 3, x plus 1 to the negative 4. I think I already see the pattern. When it's the first derivative, that power is the same as the order of the derivative. That's the first derivative, that's a 1. That's a second derivative, that's a 2. That's a third derivative, that's a 3. That's a fourth derivative, and that's a 4. But they're all negative. So for the fourth derivative, or the nth derivative, excuse me, we'll have a 1 plus x to the negative n, because the order of the derivative and that exponent match. Now we've got a factorial coming out front. That's a 3 factorial when that's a 4. That's a 2 factorial when that's a 3. That's a 1 factorial when that's a 2. And a 0 factorial, which is 1, when that's a 1. So this is an n minus 1 factorial. And now this only goes back to the first derivative. It doesn't work when n equals 0. So this is for n greater than or equal to 1, where n is an integer. And then we also have an alternating sign. It starts positive, but then it's negative, then it's positive, then it's negative. So we'll have a negative 1 to the n there. When n equals 1, we need it to be positive. So actually I think that has to be a negative 1 to the n plus 1. So we have a negative 1 squared for that first derivative. Okay. So this is the nth derivative of our function, and we need to maximize this on the interval from 0 to 0.5. So we've got the nth derivative evaluated at 0.5, or excuse me, the nth error term evaluated at x equals 0.5. We know that that's less than or equal to 0.5 to the n plus 1. And then the maximum of the absolute value of the n plus 1th derivative. So actually, let's replace all these n's with n plus 1's. So we're going to have n plus 1 plus 1, so it's going to be n plus 2. And then if I replace the n with an n plus 1, that'll just be an n factorial there, over 1 plus x to the n plus 1. We're maximizing on the interval from 0 to 0.5 for our x values. And we're dividing all of this by, according to our formula, n plus 1 factorial. Now that absolute value is going to get rid of that alternating part, and n factorial doesn't depend on x. So I've got 0.5 to the n plus 1 times n factorial, and then I've got an n plus 1 factorial down here, so that's n plus 1 times n factorial, so those reduce. And now I just need the maximum value of 1 over 1 plus x to the n plus 1 for x on the interval from 0 to 0.5. Now, all of these functions for the various values of n, starting with n equals 1, 2, 3, and so on, all these functions have the same basic shape. This function has an asymptote at x equals -1, because that's when the denominator would be 0. And then if I'm to the right of -1, let's say at x equals 0, I get a positive 1. And we'll see this. If we're to the left of -1, we see something like this. So if we're on the interval from 0 to 0.5, and they all have basically the same shape, the maximum value of that function on the interval from 0 to 0.5 is going to be 1. Because if they all have the same shape, but I plug in 0 for all of them and I get 1 on all of them, doesn't matter what n is, the maximum is going to occur right here because that function is decreasing on the interval from 0 to 0.5. So that's great. So this error is bounded by this. We've got 0.5 to the n plus 1, and then the maximum of that is 1 divided by n plus 1. And I need that expression to be less than let's see, what did they ask us to do? They want the degree of the polynomial so that the error is less than 0.0001. Ooh, that's actually kind of hard. So I've got 0.5 to the n plus 1, so it's 1/2 to the n plus 1, and I need that to be less than n plus 1 to the 0, or times 0.01. Now, this is conceptually not a difficult concept, or this is conceptually not difficult at all. Algebraically, it's difficult because you've got an exponential expression over here, and you have sort of a linear expression over here. So the best way to solve this is numerically using a graphing calculator, and most of the time we don't do that in this class. But we could use a graphing calculator in this case. It would make a lot of sense to use a graphing calculator in this case. So I'm just going to draw a couple of pictures for you. This is 1/2 to the n plus 1. So that's a problem for Calc 3, sorry about that. if I'm comparing 1/2 to the n plus 1 to this other function, 0.0001 times n plus 1, it's going to be very similar to comparing that exponential function to this linear function. The only difference is this is evaluated at integers n, actually positive integers n, and this is evaluated at all real x values. But we know how this is going to behave. When x equals -1 here, we're going to get +1 for y. When x equals 0, we're going to get 1/2. And that graph looks like this. And this is another graph, 0.0001 times x plus 0.0001. So that's a line that goes through the y-axis at 0.0001, and it has a tiny, tiny positive slope. So this is not just scale, but that's y equals 0.0001x plus 0.0001. What we're looking for is that point of intersection. Like, what is that x value for which this exponential is less than that line? I need that point of intersection. So to find that point of intersection, I'm going to use a graphing calculator online. I'm going to use Desmos to approximate these two functions. And I'm just going to look at the picture online. So I have f of x equals 0.5 to the x plus 1. And then I'll have g of x equals 0.0001 times x plus 0.0001. And then I'm going to zoom way out. And I'm looking for a point of intersection. Or maybe I'm actually zooming way in. Even on my graphing calculator, it's difficult to see where those two lines, or where those two curves cross. But I'm going to find that x value. Actually, I'm going to go to Wolfram now. I'm just going to ask it to solve for me. Solve 0.5 to the x plus 1 equals 0.0001x plus 0.0001. And they gave me an approximation. They said x is equal to 8.97 approximately. So what was that question again? Let's go back to the original question. I lost it. So our question said, find the degree of the Maclaurin polynomial required for the error of the approximation at the indicated value of x to be less than 0.001. And we realized that the error would be less than 0.001 whenever 0.5 to the n plus 1 is less than 0.0001 times x plus 1. Or n plus 1, excuse me. And we can solve that numerically, solve this inequality numerically, and we get n is approximately 8.97. So it looks like we need a 9th degree polynomial to get an error that good, because we need n to be greater than or equal to that number. So the degree of the polynomial is 9. So you're saying to yourself, well, what does that mean? This pattern continues of an x to the 6th over, or minus x to the 6th over 6 factorial, or x to the 6 over 6 plus x to the 7th over 7 minus x to the 8th over 8 plus x to the 9th over 9 plus higher degree terms. We need a lot of terms this time. It turns out that in order to have an error less than 0.0001, we need 9 terms to approximate this function to an error of less than 0.0001 at x equals 0.5.